Hello guys, welcome to my YouTube channel. In this video, we will see how we can implement logistic regression and apply gradient descent to our logistic regression from scratch using Python without using any inbuilt machine learning libraries. Okay, so let's start. The dataset I am using here is for breast classification. Okay, and the problem here is to classify the data points, given data points between two classes, whether the tumor is malignant or benign. Okay, so the link to the data set is provided in this notebook. I will upload this notebook in my GitHub and then provide the link in the description as well. Okay, so I have imported some libraries required to work with. This is just a classification report. We will see what are the precision and recall values and the F1 score in the end. So I'm just importing the libraries and I am reading the dataset. Okay, here I have downloaded the dataset, the CSV file in my local machine, so I am reading it from my local only. So now we will see how the data looks like. So I'll just say data.head. It will give me the top 5 rows. It has total 32 columns, and the main thing that we have to check is if there are any missing values. So how we can check that? Is null dot sum, right? So if all the columns gives us 0 values with this execution, we can be sure that there are no missing values. So we have values for each and every row for all the columns. Okay. So now that we know there are no missing values, we do not want this ID column here. So this is just some random number generated. So we will just drop this column from our data set. So how we can drop that? Data dot drop. So what I have to drop? ID. And access will be 1 because I want to drop that particular column ID and I want it to be in place. So in place equal to true, right? So now I have done away with the ID column from my dataset. So you see there is no ID. My target column here is this particular diagnosis column, wherein M indicates malignant tumor and B indicates benign tumor. So how we can check the available values for diagnosis? So for that, we'll see data dot. There is a function called as value counts. We can apply this on diagnosis column. Okay. So if we just execute it, you will see B benign 357 records associated with benign and 212 records are associated with malignant class. Okay. So this is how the data looks like. Now we have to separate our X and Y's, correct? So let's do that. Before that, we have to convert this M and B into 1 and 0. Okay. So let's think malignant as positive class, class 1, and benign as class 0. Okay. So let's convert that. So how we can do that? All we have to do is data of diagnosis dot replace. So I have to replace M, right? M with 1 and B with 0, correct? And I want this to be in place. So in place is equal to true. So now if I check data, if I just execute this once more, I will see instead of M and B, I will see 1 and 0. Okay. So M had 212 values. Now M is converted into 1. So 212 values. Similarly, for benign, it is 0 and we have 357 values for that. Now we will separate out our X's and Y's. So how we can do that? All we have to do is X is equal to data dot. I do not want my diagnosis column to be part of my features. Okay, so I will just drop it. Diagnosis, I will say access is equal to 1. Okay, but I do not want it to be in place, so I do not want to affect the original data point. I want to have diagnosis column in my data frame, but I do not want it to be part of my X variable. Okay, so that's it. Now I want to convert it into numpy array. I do not want it to be a data frame because I will be dealing with matrix multiplication and all. So I want X to be my numpy array. So if I just say 2 numpy, it will convert the data frame without this diagnosis column into a numpy array. Okay. Now I will need Y. So what is my Y? It is data of diagnosis, right? And so we have to just say values to get the Y into numpy array format. So if I just execute it and x dot shape, we have 569 records and 30 columns. Earlier we had 31 columns, but we done away with diagnosis column for our features, right? So that's the reason we have 30 columns here. And then if I check y dot shape, it will be 569 because we have 569 records. So now that we are done with separating x and y's, we want our feature x0 whose value is 1 for all the records, correct? So how we can do that? All we have to do is x is equal to np dot c, it's called as column stack, np dot ones, length of x, comma x. So now if I say x dot say, you will see instead of 30 we have 31 columns. The first column is all ones. How many ones? 569 ones, right? So that's the length of x. Now that we have done the transformation required, we want our x, the data, the features to be in a different format. So in what format we want? We want to represent each row, each column as one training example. So right now each row is a training example. Now we want it to be transpose of this. So how we can do that? X is equal to x dot t, right? Now if I check the shape of x, it will be 31 rows and 569 columns. So each column is my one training example, right? Now we have done whatever required for having our x and y in the required format and required data type, that is numpy array. There are few things which I had to discuss because the values are in some tens and in hundreds, and also you can see less than 1, right? So we will not go with in-depth discussion on scaling and other stuffs. We will use this data as it is and see how our logistic regression and gradient descent performs on this data set. I will be covering the feature scaling and normalization of the features in my separate video where I'll talk about the importance of the scaling and normalization. Okay. So now we will use the data as it is. We will not scale or normalize any of the data here, right? Now, in order to compute the hypothesis, I will define a separate function. I will call it as define compute hypothesis, and the inputs for this are parameters, learnable parameters, and my x, correct? So my hypothesis is for sigmoid function, it is 1 by 1 plus e to the power minus theta transpose x, correct? So this is my sigmoid function. So we have to implement this part now. So what I'll do, I'll separate this theta transpose x into one variable, then I'll apply this whole formula on that particular variable. So how I can do that? I have to do is, I'll call the theta transpose x as z. Z is equal to np dot matmul, okay, params dot t, that is my theta transpose, and comma x. So these two are our matrices, and np dot matmul is the method used for matrix multiplication. So now that we have our z, we will get our predictions is equal to 1 divided by 1 plus e to the power minus theta transpose x, right? Now theta transpose x is z. So 1 plus, how we can compute e power? All we have to do is np dot exp, okay, and say minus z. So this is our 1 by 1 plus e to the power minus theta transpose x. So now we have our predictions. I will return this predictions, okay. So now we are done with defining our compute hypothesis function, right? Now I have to implement my cost function, right? So what is the cost for logistic regression? It is derived from the principle of maximum likelihood. This is also called as cross entropy loss, right? I have given it here, minus 1 by n summation from I1 to m yi log of h theta of xi plus 1 minus yi log h theta 1 minus log h theta of xi, okay. So let us implement this particular part in this function, okay. Now I'll name this as define compute cost. So what all are the required things in this? We need predictions and actual values, correct? So these are the only two required things. If we require anything else, we will do that while implementing the function, right? So first we will take the value m, that is the number of training examples. We can take them by length of actual numpy array. So that is 569, right? So m will have 569 value. Now that we have m, we need to implement these particular things in our Python code. So what I'll do is, I will have log of this hypothesis in one variable, okay, and log of 1 minus hypothesis in another variable, so that it will be easy for us to combine everything as a whole, okay. So I'll say, I'll just name it as log of hypothesis, or let's say log of predictions, okay, is equal to np dot log of predictions, okay. So this will give me this particular part, log of predictions, okay. Now I need log of 1 minus predictions. So how I can do that? I'll create another variable, log of, I'll just name it as it is, 1 minus predictions. So it will be easy for us to understand while we put that in a bigger formula, okay. So how I can do that? It is np dot log of 1 minus predictions, okay. So this is this particular part. All I have to do is, I have to use these two variables that I created and combine everything as one, okay. So how I can do that? So all I have to do is, I have to say, let's say cost is equal to, the first one is minus 1 by m, correct? So minus 1 by m into, so what is it? Yi into log of h theta of xi. So this is log of predictions, correct? So it is actual into log of predictions, right? So this is my first part, actual into log of predictions plus 1 minus actual, right? 1 minus actual into, what is it? Log of 1 minus predictions. So it is this particular variable into log of 1 minus predictions, correct? So this whole thing is the plus, right? Now that we have this, we need to sum on whole this particular part, right? So all I have to do is np dot sum, correct? So if I just check it, it will be, I need another bracket, right? So np dot sum, and I need to enclose it here. So let's check the brackets. This is closed here, this is closed here, and this part is closed here, right? Now this is getting closed here, whole thing, and I need to close for np dot sum. So let's close another bracket. So my cost function is ready. This is my ultimate cost. Now I will just say return cost from here, okay. So this is the definition of cost function. We will verify each method in the later part. Now what I have to do is, I have to implement my gradient descent algorithm. So if you just know the gradient descent algorithm, it goes something like this. We need to update the parameters for multiple iterations till we converge to a global minimum point, okay. So for that, the gradient descent doesn't differ much from what we have implemented in linear regression, but the thing that differs is this particular hypothesis. This hypothesis is our sigmoid function, right? So let's implement the gradient descent now. So how we can implement it? All we have to do is, I will say define gradient descent, and what are the things required? We need x, we need y, we need learning rate, we need number of iterations, okay. We need to run this step for some iterations, right? So those are the things. I will assign y to my actual variable, I will create a list of costs wherein I will be storing the cost at each and every iteration. I will also create a list called accuracies. So this variable holds the accuracy of my gradient descent or logistic regression as a whole at each iteration. Okay, we will see how this works, how this comes out. Okay, now we need to initialize our parameters, right? So the first step is initialize our parameters. So how many parameters we will have? As many number of features that we have. So how we can do that? Params is equal to np dot zeros. So how many zeros we want? X dot shape of 0, right? So if you check the shape of x, we have 31 features, right, including our x0. So those many parameters we want. These are our learnable parameters. So we have 31 learnable parameters in this case. Okay. Now in this formula, we have something called as m, right? This particular m is number of training examples. So we need that m also to be created. M is equal to just a length of actual. So how many training examples we have? We will have so many actual numbers. So those will be the number of our training examples, and I am treating it as a variable m. Okay. So this is my m. Now for I in range of iterations. So what I have to do? I have to have my predictions is equal to compute hypothesis. So this compute hypothesis is here. It takes parameters and x as the arguments, right? Params and x, correct? Now I will, these predictions are the probability that the given x belongs to class 1. Since it's a probability, we have to convert the probabilities into actual classes. So if you just remember from my logistic regression video, the probabilities which are greater than or equal to 0.5 will be treated as belonging to class 1, that is malignant. If the prediction or the predicted probability is less than 0.5, we will treat those as belonging to class 0 or benign. Okay. So for that, we will create another method, right? And we will call it as predict classes. Okay. So I'll just, okay, I can have it here, or I'll move it. I will have it here. So after I compute hypothesis, I need to predict my classes, right? So I will say predict classes. Now this is define predict classes. It will take predictions as an argument. Then predicted classes is equal to, initially I will initialize everything to 0. np dot zeros, length of predictions. Okay. Then using numpy np dot where, I will just convert all the values greater than or equal to 0.5 to 1. Rest remaining things will remain 0 because it has all zeros everywhere. So all I have to do is predicted classes of np dot where predictions is greater than or equal to 0.5. I will assign those indices to 1. That's it. So this will return me a numpire of true and false boolean values. Wherever this condition is true, at those particular indices, that element will be set to 1. Otherwise, it will be left as 0, because this is the initially predicted classes is a numpire of zeros, right? So that's it. Now I will say return predicted classes. Okay. So this is our predicted classes. Now coming to this gradient descent. Now that we have predictions, this compute hypothesis will give the probabilities, right? So we will have to convert it to the actual predicted classes. So how we can do that? I will say class predictions is equal to predict classes. So this is a recent method that we have implemented, predict classes, right? So this will take in predictions as my argument, predictions. Okay. So this is, we are done with predicting the classes. Now what I will do, I will say accuracies dot append. I need to create another method which will compute the accuracy. So I will create it here. I will name it as calculate accuracy. So I'll just mark it down. calculate accuracy. Okay, so I name it as define calculate accuracy. So what it will take? It will take class predictions and actual as the argument, right? So all I have to do is accuracy is equal to, so I'll do something here, sum of class predictions is equal to actual, okay, divided by length of actual. So what this does is, we will have 0 or 1 in our class predictions, and in actual also we will have 0 or 1. So wherever the values matches 0 to 0 or 1 to 1, those things will be converted to 1, or true will be returned at those particular indices, and those trues will be summed up. So since we can treat true as 1, the sum will be some integer, and in order to calculate the accuracy, we will divide the correct predictions, number of correct predictions, to the total number of values that we have. That is length of actual, which is 569, correct? And in the end, we can multiply it with 100 to get the accuracy. Okay. So now we are done with calculating the accuracy. I will just say return accuracy. Now I will use this method calculate accuracy to append to the accuracies list. So what I will do, I will say I will just call this calculate accuracies. Okay, then the arguments will be class predictions and actual, right? So I'll just have to pass these arguments. Now I have calculated the accuracies. Now the next step is, I need to implement this particular stuff here. This part, theta is equal to theta minus alpha into theta d theta by d partial derivatives of our cost function, right? D by d theta j. So we will implement this. Now in order to do that, I will again split this part as errors, so that it will be easy for me to accumulate everything in one equation. Okay. So how I will do that? I will just say errors is equal to predictions minus actual. Okay. This is my error term, and then I will say, now that I have my errors, I will need to compute the cost, right? So I have calculated the accuracies, I need to compute the cost. So can I compute the cost before getting the errors? Yes, I can, right? So now that I have my accuracies, I can also use my compute cost method to compute my overall cost at each iteration, right? So predictions comma actual. So this is my compute cost method. So I will be appending the cost at each iteration into this particular list. Okay. Now that I have the cost, I need to update my gradients, right? So gradients equal to 1 by m into np dot matmul x comma errors, right? I have explained about this in my video where I have implemented linear regression and applied gradient descent to it using Python from scratch. So if you guys are not sure how we arrived at this is called as vectorization. You can please revisit that video. Okay. Or you can see my vectorization video wherein I have explained how this matrix multiplication will save us the time by avoiding the for loops. Okay. So this is how we calculate the gradients. Now that we have calculated our partial derivatives, all we have to do is we have to update our parameters. So parameters equal to, my variable is params, right? So params minus learning rate into gradients, correct? Now that's it. We have updated our parameters. So it will run for so many iterations. Once it runs for so many iterations, I will just return my params, learned parameters, the costs list and accuracies list. Okay. So this is my gradient descent method. Now that we have everything that we want, we will just verify whether each of the methods that we have written here will actually work as per the requirement. Okay, so in order to do that, let's initialize the parameters, okay, and get our m ready. Okay, so how we can do that? We can say params is equal to, so this is just for verification purpose, okay, verification purpose. So I'll say params is equal to np dot zeros x dot shape of 0, and then predictions is equal to, I'll just call my compute hypothesis function to check the return type or the number of values it returns. So it takes params and x, right? So if I just execute it and then check the length of predictions, it should be 569. Okay, so we are good with compute hypothesis function, right? So similarly, we will verify our compute cost and also compute gradients, compute gradient descent or gradient descent method, right? So first we will see, in order to get the gradient descent, we need to have our hypothesis and all, right? So we will have our predictions. We already have our predictions. We will just take this, we will verify this cost function, okay? So I'll just copy this whole stuff here, okay? So m is my length of actual, or I can say length of y, because actual is only within the functions that will fail. So y is nothing but my actual, right? So now I am getting log of predictions, np dot log of predictions. I have my predictions here, and yes, instead of this, I'll just create a variable, because otherwise I have to change it multiple times. So now that I have everything, we'll see. It says name log predictions is not defined. Log of predictions, right? It should be. So it should be log of predictions. Now if I check the cost, so it is 0.6931. So it is returning a single value. So we are fine with our cost function. Now that we have verified our cost function, we have to verify our gradient descent, right? So for that, what all things we need? We need our learning rate. Let's assign to some small value, okay? And then we have our predictions already, so I will not call that. Let me just take my errors. So we need errors, right? Predictions minus actual, right? So in order to do that, I will just say errors is equal to predictions minus actual. Now that I have my errors, I will have this gradients. So gradients is equal to 1 by m into np dot mathmal x comma errors, and then finally I need to verify this part. Okay, so params is equal to params minus learning rate into gradients. Okay, now if I execute it and check length of my gradients, it must be 31, because we have 31 learnable parameters. We need 31 gradients, and this must be, the length of this must be equal to 31. Okay, so let's check the length of parameters also. So it is 31. Now that we have verified individual functions, the main functions, gradient descent, compute hypothesis, compute cost, we are good to execute this for some 1000 iterations. Okay, so let us see that. So what I'll do here, just give me a second. So I'll just copy this. I have noted it down, the lines. So I am assigning learning rate to 0.00001. It is a very small value, and I am trying to run it for 100 iterations. Okay, and all I am doing is I am calling gradient descent. I think I have to update my cost log of predictions here. Okay, so this is log of predictions. So now that I am done with it, I will just execute it. So it says actual is not defined. So where is it? In compute cost, it says actual is not defined. So why it is saying okay, so there is a spelling mistake, CTUAL. Okay, so that should do. At least that error should go away. Okay, so we are good with it. Now that we have executed it for 100 iterations, we'll see how our cost reduced at each iteration. Okay, so if I just plot it, yeah, so you see the cost is actually oscillating between low and higher values. It is trying very hard to arrive at the global minimum point. And similarly, if I plot the accuracy and then check, it will, I think it should look somewhat like this. Yes, so accuracy will go up with each iteration and cost will come down with each iteration. That is happening fine, but the curve is not smooth. The accuracies are oscillating between high and low values very often. This is usually the indication that our learning rate is very high. Okay, because if you guys remember about the learning rate video that I have explained in my video, if it is too high, there will be a probability to overshoot the global minimum from one particular point. Instead of reaching here, we will just overshoot this point and then reach to the other end, which will be more the cost will be more than what we need to achieve at the global minimum. Okay, so that's the reason we see some oscillations here. So in order to avoid this, what we can do is we can reduce the learning rate and see its effect. So if I just execute it again and then see the cost function is getting smoother and smoother. Okay, so now if I just check the accuracy also, see, as the iteration increases, the accuracy is also increasing. Okay, now that we have this, let's execute it for some 500 iterations. Okay, and see how our accuracy improves and the cost reduces further. So the minimum cost that we have is around 0.63 with 100 iterations. Now with 500 iterations, so we can see the cost is reducing further. Earlier it was around 0.63, the final cost. Now it is around 0.525, right? So similarly, if we check the accuracy, it was around 65 or nearly 65, right? So if I check it now, you see the accuracy has increased very much. It is almost nearly 90, right? So now that we have increased it to 500, let's do it for 1000 iterations for one final time and then check how this works. Okay, so I'll just execute my gradient descent for 1000 iterations. Okay, now that I have executed it, you see the cost is reducing gradually. Earlier it was stopping at 0.52 somewhere with our 500 iterations. Now it is coming down to 0.45. Okay, now similarly the accuracy, okay, accuracy is not improving further. It is nearly 90, 91 somewhere like this. So we will see the initial accuracy and final accuracy in our accuracies list, right? So we have a list of accuracies at each iteration. So we can check that. So at my first iteration, accuracy was 37%, right? And at my last iteration, accuracy is 90.68. So you see, at each iteration, we are seeing improvement in the accuracy and also the cost is getting reduced, right? This is how we want our cost and accuracy graphs to look like. This is also called as learning curves. If you just club both in one graph, you will see one coming down and accuracy going in the other direction towards upside, right? So this is how our graphs should look like. Okay, now that we have seen it, so we are good with all our verification part and the experimentation part. So you can actually implement this by understanding the video and the code that I have given here, so that it will be a good learning for you guys. That's it for this video. If you guys have any questions on this, reach out to me via comment section. I will try to get back to you with the answers, and I will provide the link to my GitHub for this particular notebook. You guys can have a look at it and learn to code the logistic regression and implement gradient descent from scratch. Okay, so that's it for this video. Hope you guys understood and learned something. Thanks. Till we see in the next video. Bye bye.